Good afternoon. And for this, we are presenting our problem situation, presented by Alessandra Hernandez Bolaños and your server, Carla Paola Ramirez Islas. In this problem situation that we are presented, we are asked to provide a solution for a real situation using the knowledge acquired. Likewise, some questions related to these topics will be answered to get deeper into these topics, and thus, we have a clear idea of the topics we are dealing with. Throughout these last weeks, we have seen topics related to the signal conditioning system, which will be now applied.
Before we get started, it's important to mention that I am gonna say the answer to summarize because of time. And well, a signal condition can be defined as a process to obtain data. This will be done from an amplification of a signal, and this will be covered into a comparative format for data acquisition or machine control. Some of the characteristics that make this process necessary include the signal can be very small and it requires amplification. It can have interference and must be eliminated, or it can be a nonlinear and require alignment among other factors. Well, it can be presented in inverting amplifier and differential amplifier. In these two images, we can appreciate this behavior in each amplifier. We can summarize the signal condition guarantees the accuracy of measurements. Signal condition protects desired signal from unwanted components or effects using isolation or filtering. In this slide, we only put some of the features which are that they can combine active and passive components like resistors, capacitors, and inductors. They can allow cascade connections. It's economically feasible compared to another types of assemblies. And if the circuit has an operational amplifier, the voltage is limited by the saturation voltage of these elements. Well, it is for obtaining an equation that satisfies the parameters or approximations. The most mathematical approximations used for active filters are elliptic, Butterworth, Thompson, and Chebyshev. We must take into consideration that we seek to reduce cost, time, size, and list of materials. According to several designers, the most suitable device must be chosen, and we have to know the full potential that it has. Then all the calculations must be with mathematical representations. Subsequently, we must generate some diagrams and from there simulations just to see if the requirements are met. Finally, we can verify with the use of simulators or visualization on an oscilloscope.
Next. We are asked to help Jorge Calderon to design a signal conditioning system for a new CO2 monitor. This monitor provides a linear response with readings indicated that 0% of CO2, the sensor delivers -1 volts, while at 100%, the sensor delivers 5 volts. The signal conditioner to be designed requires that the circuit delivers -3 volts at 0% of CO2 and 3 volts at 100% of CO2. Additionally, the signal must be filtered with an active low-pass filter of second order Butterworth with a cutoff frequencies equal to 50 Hz. The operational amplifiers must be powered with 5 volts. And with this, we obtain the following diagram. For linear representation, we can use the slope equation to obtain the equation for this graph. To obtain the value of M and B, we need a first point for BI -1 and -3 in this case, and for the second point, we need the voltage of out, which is 5 and 3. Thus, the voltage of out is obtained. And with the previous points, we are obtaining this graph. And now it's needed to obtain the slope, being the M, the following formula, and Now we substitute and obtain that m equals to 1, meanwhile b equals to -2. Obtaining that the equation for the out voltage, it's the in voltage minus 2 volts. Next. By this, we need a -2 volts displacement in the in voltage, meaning that a voltage divider op-amp is needed, which is now shown. The equation for this type of op-amps, which is now shown, and by supposing that we have R2 equals to R4 and R1 equals to R3, we end up with the following equation. And after analyzing this equation, we can make the assumption that every resistance presented in this project has the value of 1K volts. The reason behind this is that the gain presented inside the equation. To fulfill the desired operation range, we need to reduce the signal by 2, and using the resistance, we can keep in mind that the resistance is in fact the gain being multiplied by the voltage. And we need to keep the second voltage as the same. Meanwhile, the first voltage is translated as the 2 volts that we are reducing from the original signal. And to prove this last, the circuit was simulated with the op-amps. Finally, we need to clear up the signal received, and by clearing the signals that pass over 50 Hz, it's necessary to establish a second-order low-pass filter with a frequency cut of 50 Hz. To make it true, we propose the capacitance of 10 microfarads, and we use the equation provided to calculate the resistance needed in this case, which is now shown. And we replace the values, getting that our resistance is 318.3 ohms. And now we can make the simulation, which is now shown. And finally, we up our 2 diagrams for our 2 simulations. Next. Ended with this on the final signal conditional system. And thank you for your attention.